Welcome! Today we're diving into the foundational concepts behind motion control, PID control and kinematics. This is an advanced topic and entirely optional. You don't need to understand any of this if you just want to use the Polaris driver by itself. However, if you want to diagnose poor tracking, or you're curious about how the system works under the hood, or you want to tune up its performance, then this walkthrough is for you. We're going to cover 4 topics. Each one adds an extra layer of understanding and, unfortunately, complexity. The first topic we'll cover is steady state. We'll look at what good steady state sidereal tracking looks like in the PID controller so you can understand when things are going well. The next topic is kinematics. We'll explore kinematics and how the PID controller fits into the wider control system inside the Alpaca driver. The next topic is dynamics, and we'll see how the PID controller reacts to the various control inputs like go-tos, slews, pulse guiding, or orbitals. And finally, we'll explore tuning, how to get the best performance out of the PID controller by changing some of its parameters. So first up, to diagnose tracking performance, we can use the side menu and choose the PID tuning page. Now, don't be intimidated by all these charts. I'm going to walk you through each of these and you'll be an expert in no time. So to tell how well the mount is tracking sidereal motion, the first thing to check is the RMS error on each of the axes. There's 3 numbers here. And RMS stands for root mean square. It's a way of measuring how far the mount's position deviates from where it's supposed to be. Think of it as a running average of how far off the mount is, measured in arc seconds. Now the lower these numbers are, the better. Now, if it's under 3 arc seconds, that's considered very good. It means that a mount is staying very closely to its intended position. Now beyond that, if we look at these charts, each one represents each of the 3 axes in equatorial coordinates when you call them up. And with sidereal motion, you expect that the set point, or the target, to be flat, steady and horizontal. That's the green line here. That's the target it's trying to control it to. And the white line that's zigging around is the actual position for that particular coordinate. We can, just to make it a bit easier, we'll go to topocentric coordinates. These are the azimuth, altitude and roll we're probably more familiar with. And here you can see that the target that we're trying to control to for the azimuth is slowly decreasing, and the altitude is also slowly decreasing, and the roll angle is also slowly decreasing at a certain rate. And what you want to look for in these top charts is you want the white line, which is the actual position, to be very closely tracking the green line, which is the target position. Ideally, the white line is underneath the green line, and the less deviation, the better. The other things you'll notice is that both of the lines, they should be straight. So be aware of any oscillations, big swings, zigzags. They give you an indication that there's something wrong with the tracking. Now the motor angles is the 3rd set of coordinates. Now these will typically be following the azimuth, altitude and roll coordinates unless the roll angle is non-zero. And they should also be straight lines. Now one thing to notice here on this M3 angle, it looks like it's a bit out of control here, but when you look at the RMS error, it's 1.3 arc seconds, which is really good. All this means is that this is actually slowly moving, slowly changing, and it's zoomed in and you can sort of see a very fine detail, but overall this is still a very good indication. In fact, these numbers here show it's tracking very well. If we pop back to equatorial coordinates, again, even though the white line is going up and down, the fact that the RMS is so small, this is actually very, very good tracking. Now the bottom charts, each of these bottom charts, again one for each of the axes, they indicate how the mount's motors are working to keep things stable. These are velocity charts, and they show how fast each motor is turning to adjust the mount's position. Now if we look at one of them, behind the scenes what's actually happening is the mount uses a control system to decide how fast to move each motor, and it blends 4 different signals to work out the speed of the motor. The first one is KP. This is the proportional response, this magenta line, and it basically is proportional to how far you're off, so how far you're deviating from the set point. This will either increase to correct it or decrease it to bring it back in line. The second one, which is the olive line, this is the integral response. It's how far you've been off the target. So the longer you've been off or underneath the set point, the larger this thing will grow. It'll integrate up and become larger. The third one is KD, which is the derivative response, and it tends to dampen out any fast movement. So the faster you're going, the faster the output for the motor speed, the larger this will be in the opposite direction, and it helps to reduce oscillations. Now the cyan line is the output, and that's the speed of the motor that we're asking it to travel at, and the green line is a feedforward, which is you can think of it like the set point for speed. This is the speed that we want the motor to be going at if we're keeping to sidereal motion. So it works out what that speed is. So for motor 1, it should be travelling in minus 0.0025 degrees per second. Motor 2 needs to be travelling at minus 0.0035 degrees per second. And motor 3, very barely, it should be travelling at 0.0003 degrees per second in the opposite direction, very slowly. That's why these lines look very unstable here, but actually it's so zoomed in. The standard deviation is only 0.82 arc seconds, which is actually fantastic. So the coloured lines show how each part of the control system contributes to the output. So these 4 lines, the magenta one, the olive one, the orange one, and the green one, are all added together to calculate what this cyan output signal. Good tracking on the bottom velocity charts. You should see the cyan closely following the green line, and there should be little deviation between the cyan and the green line. Ideally it's on top of it and it's tracking flat and horizontal. The magenta line, you want it to be hovering around the 0 mark on each of these axes, and it should on average be 0. So this indicates that the position is neither above or below what the set point is. It's sort of hovering around there as well. Now the brown line, it should be straight and flat too. It should be mirroring the cyan line. So this brown line up the top will be a proportion of whatever your cyan line is. It's just mirrored onto the other side. So whatever your velocity of the motor is, there will be a dampening factor on the opposite direction. And the olive line, you expect it to be flat as well, straight and flat. All of these lines should be straight and flat. You can see there's a bit of a perturbance here in motor 2, but it's corrected it and brought it back straight and flat, and it's tracking well. So that image, we might have had a slight extra friction on the gear, and it had to counteract it and bring it back into line. So all of the velocity graphs, you might see a little sawtooth, but they should not be erratic. They should be nice and smooth. There shouldn't be any spikes or wild swings or oscillations. That means if it's nice and steady like this, that the mount isn't overcorrecting or jittering. It's making a calm, precise adjustments to stay in track. So if you ever have problems with the tracking, come to this page, have a look at these charts, look at the RMS error, check that they're nice and low, and check that all the lines are steady and straight. If they're not, then you might have to unfortunately throw away a few of your subs and only take the good ones. In the next section, we'll move on to talking about the kinematics, which can be found on this page here. So the reason I want to talk about this before we go into tuning is I want to describe how the PID controller fits into the overall control system. So kinematics is the study of how things move without worrying about what causes the motion. in the context of the driver, it's all about tracking orientation and velocity over time across different coordinate systems. This allows the driver to rotate the telescope smoothly across the sky and respond to any of the different control inputs that we have. Now this page displays a high-level data flow diagram on the right, along with corresponding coordinates at each of the numbered stages on the left. If you're looking at the open source code, you will actually see reference to these Greek letter names: zeta, theta, iota, delta, alpha, omega. They are within the code and will help you give you an understanding of what that actual variable is representing. So let's walk through the diagram. What happens is up the top we've got the Polaris mount, and it continuously senses the orientation and sends telemetry down through the driver every 200 milliseconds. From this data, the driver calculates two things: where the Polaris thinks it's pointing and where the motors are actually positioned. These coordinates are passed through the Kalman filter, which we talked about in the previous video, and using the multi-point alignment result in a more accurate orientated estimate, both in equatorial and geographic coordinates. And they are presented as the PV for short, which is present value. Now applications like NINA, CCDL, PHD2, they send movement commands such as a go-to, slew, a pulse guide, and it translates them into a change in the set point. And the set point represents the desired position for each of the coordinates that we're asking the mount to follow or track. Now the difference between the set point and the process value is called an error signal, and this error signal is used to calculate the different components of the PID controller that we looked at in the previous section. There's the proportional component, the integrative component, the derivative component. Along the side, with orbitals and with the other tracking rates, we calculate what the desired velocity of each of the motors should be as well, and we feed that forward into the PID controller too. And the PID controller adds all of these values up together and determines a motor speed that should be used to drive each of the three motors within the Polaris head. And it passes those motor speeds onto the motor speed controller, which we've hopefully calibrated, and then it translates those motor speeds into actual commands that it sends down to the Polaris, telling it to move the joystick left, right, slow speed 1, 2, 3, 4, 5. That's basically how it works. So we basically get the orientation from the Polaris, we filter it, do some adjustments for the alignment, we store that as the PV, we take commands from all of the Alpaca applications and they adjust the set point. We feed that into the components of the PID controller, does some smart calculations, works out how fast the motor should be moving, and sends out commands to the Polaris. So that's it in a nutshell. That's how the system works. Today we're going to talk about the dynamics of the PID controller and how to tune it to get better performance out of your mount. And we'll start the journey by looking at our PID tuning page that gives an overview of each of the axes. And you may have noticed that there's a tune button on each of these. And if you click on one of them, it takes you to a detail page for that particular axis. On this page, you can change the coordinate systems just like you did on the overview page. You can also change which axis you're actually looking at a particular time. On this page, you're really only looking at one axis, and on the left, you've got your position chart, and on the right, you've got your velocity chart. It's pretty much the same data, but you've also got the ability to make some fine adjustments to some of the parameters in the PID tune. Not only, as well as the adjustments, you can also run some little tests to monitor how the PID controller reacts to different types of inputs via the Alpaca protocol. And we've got a range of test cases, varying sizes of go-tos, of different slew rates, and also we simulate some pulse guiding from PHD2. Run a couple of these and we'll see how the controller reacts. So we'll start off with a 5-degree go-to. So if you issued a go-to on, we'll put it onto motor 1. If you issued it's currently tracking, by the way. We might actually, we'll turn off tracking, we'll see what happens there. You'll notice immediately that the motor stops moving and there's a bit of backlash that it just sort of slips and it doesn't bother about. When it's in idle mode, it's not trying to control this and reduce the difference between the set point and the PV. It's just letting it go wherever it is. Now if we hit go to 5 degrees, what we should see is a jump in the set point of 5 degrees. There we go. And we see that the motor controller, the PID controller, had a big gap in the proportional, which caused the speed to accelerate up. And then once it got halfway, it thought, oh, I better start slowing down. And you see the response where the position sort of ramped up and stabilized around the new position, and it's gone back into idle again. So let's do a bigger jump. Let's choose a 90-degree jump, and let's watch what happens here. We should see the set point jump up to 90 degrees, and we should see the speed ramp up, and it hits a maximum of how fast the motor can go, which is about 8.5 or 9 degrees per second, and when it gets closer it should slow down. You may encounter this problem where we've hit the anti-wind-up limit. You'll definitely probably hit it if you start tracking satellites because they spin them out around quite a bit. Don't forget, all you need to do is click review, see which motor limit you've exceeded. That's that particular one. And you can click to acknowledge, and then we'll just hit home. That should bring them out. See, this motor 1 was very high, it's going to bring that back to 0. Now there are a couple of global parameters that you can change here. One is the maximum output acceleration rate. So this is how fast it ramps up and slows down in speed. And the next one is what is the maximum slew velocity. Again, if you leave that at 0, that's the maximum do based on your calibration. So what we might do is I might just show you how these change. So we'll do a 45-degree jump and we'll watch what happens. If you watch here, if you look at the slope that it goes up and see the maximum that it goes up to about 8 degrees, and it's got a slope, I think, about 3. So what we'll do is we'll change this. We'll make it so that it can only accelerate at 1 degree per second squared, and the maximum speed we're going to limit it to, say, 5. Let's do the same thing, and you'll notice that the ramp is a lot slower, so it more slowly accelerates up, and the maximum speed it gets to is 5 rather than 9, and then it'll slowly come back down again. So if you want to drain your battery less and have a less responsive mount, you can change these properties here, but I recommend just leaving them at the defaults. In fact, we'll put them back to the defaults. Let's just wind them back to 0. Now the next type of test that we can perform is a slew. We'll choose a slew of 0.2 degrees per second, and if you hold down this button here, we should see the set point changing, and it's only changing 0.2 degrees per second, and we can see that the set point sort of is moving up on a steady ramp. Let's try 1 degree per second. That's better. It's easier to see. So you can see while I'm holding that down, the set point is changing at 1 degree per second, ramping up, the PV trailing behind it, and on the velocity chart you can see that the set point for the velocity has gone up to 1, and you can see that the output is closely tracking it. Nice steady state there. And the final one we'll look at is for a pulse input. Now when we get a nudge from PHD2, what it does is it chooses us to move at a faster rate for a certain amount of time. So in this case it's 2 seconds, and the rate it's asking us to move at is set by the right ascension pulse guide rate, and in this case it's 1 times the sidereal, and the declination is 1 times the sidereal. We might change that to half sidereal. So that means when we get a pulse, we want to go at a current rate plus an extra half a sidereal rate in that direction. So we'll go back into the tuning, And we'll stay on equatorial, and let's do a pulse of 2 seconds. That looks good. It's got a low RMS, so it's tracking well, and we'll do a pulse. This should shift. You should see a jump in the speed, and you should see a step in the set point, a ramp up in the set point. So here's the pulse. So it asked it to go a bit faster for that particular amount of time, and during that time we ramped up the set point. If we go back down again, it'll bring it back to where it was previously. So these are the pulses in velocity that we're seeing, and if we do a very short pulse, let's say a 200 millisecond pulse, you can see we had a little bump there we'll do another one, and you can see the effect it has on the set point. So if the PHD2 sees that we're slipping away from the star, it might go bump, 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 and push the tracking so that we're moving slightly in the RA direction. Or it might even change the declination. So if you've got a guide scope running, you might actually see when you're looking at the PID tuning page, you'll see this actually going up and down based on the guide star and the inputs that we're getting from the guiding application, whichever one you use. So there are the three types of dynamic inputs that we've got as test cases. And the trick with tuning is you want to make sure that the tuning settings that you have are suitable for each of these three types of cases. So for large go-tos, you might actually, if you want to optimize for that, you might have slightly different settings than for different slew rates, or for pulse guiding, or in the steady state tracking of sidereal or other type of motion. So what we're going to do here now is I'm going to move to the motor coordinates, and I'm going to show you what happens when we look at, say, motor 1 and adjust some of the parameters that we've got here. So the first thing, if we had a new system and we didn't have any defaults, to start tuning, I would recommend turning off the dampening and the integrative, so that all we have is proportional control. And this means that when there's a deviation between the set point and the output, the magenta line is going to try and counteract that deviation and bring the mount back in line. And you can see here that as the mount has deviated in velocity, it says, oh, I need to bring it down, so it pulls it down, it goes too far, and then we've got a bit of a sine wave happening here. And you can see it's sort of slowing it down, but we've got a bit of a problem. So typically you'll start at a low value of the proportional gain, and you'll notice that we're tracking better here. It's actually still tracking pretty well with a low gain in that, but if we do a go-to, let's issue a go-to, you can see that it's not speeding up as quickly as it could to get up to the desired position. In fact, it's taken quite a while for us to get there. And what we want to do is we probably want to have a higher velocity to get up there more quickly. And the way we can do that is by increasing the proportional. We'll do the step again and see how it accelerated more quickly, and it's gone a bit over the rump. If we go and increase this even further, extreme, say 1.5, and do a step, it will accelerate very quickly and it'll overshoot the step, and it'll come back down and go back up again. If you see these sorts of oscillations, you know you've gone too far in the proportional gain. So that's probably too high. It's getting too aggressive going up and going too far, going down and too far. It'll eventually get there, but this is something that you probably don't want. So that's a good indication that you've gone too far with the proportional gain. So we'll bring that back down. We know that around about 1 is probably a good setting to have. Now let's do the step again. And you notice here it's still, even at a gain of 1, it's overshooting and going too far. So that's where the dampening and the derivative gain can come into effect. if you increase the dampening, what it'll do is the faster that the mount is going, the more dampening and slowing effect. So what will happen is as it's getting up, and we'll just do one, let's watch what happens in the effect it has. It should help tamper that, and that looks much better. It stopped it overshooting, and the reason it does that is you can see as the speed goes up, we get this negative effect, and it cuts back the top of the proportional gain, and it means that you're slowing down at this midpoint so that you're not going to overshoot, and that has a good dampening effect. And what I've found is having KD around about a half of KP is probably a good idea, and that helps to allow you to have an aggressive proportional gain but dampen the response so that you're not oscillating. Now the other thing you'll notice here is when I do, say, a ramp, let's do a slow ramp, you'll notice because I've got Ki as set to 0, there's no Ki component in the PID control, and I'll show you the effect that has at the moment. Now when I ramp, there we go, that's better. Now notice as I'm ramping, as I'm slowing at a very slow rate here, 0.006 degrees per second, notice how the PV is trailing. It's sort of below, it's always below the set point on the left-hand chart. And the reason for that is that these values are fixed. The proportional's fixed and the speed's fixed, but it's not getting enough. It's still got a gap, and it's got a consistent gap below the set point. And that's where Ki can help, is if you increase it, let's say increase it to, you don't want to increase this one too big. What will happen is if there is a consistent gap, like it's always below, the integrative gain will increase until it closes that gap. And you can see here on the right hand side of the chart, the olive line is increasing because it's seeing a steady gap below the set point, and that increases, that has increased until it's pulled that gap down and forced this back to 0. So that's what we're seeing with the steady state previously. So the integrative is really important when you've got a steady motion and you want to close any persistent gap between the PV and the set point. And that's how these three affect each other. You can increase the KP to make it more responsive, but then you may get oscillations. You can bring in some dampening with KD to help slow the oscillations so that it doesn't go too fast and overshoot. And the integrative component can help you eliminate any persistent errors. That's what those three components can do in the tuning of those parameters. You may find that you need different settings on each of the different motors. And I've currently got them set to be all the same. But when you see your tracking, and if you see some big oscillations and your RMS error is high, you may want to consider, if it's in steady state tracking, decreasing the KP. That should reduce the oscillations, or potentially increasing the dampening. If you're seeing a consistent error, you may want to increase the integrative component. Any changes that you make to these parameters for the PID tuning, they will take effect immediately, and they're not persistent if you restart the driver. If you find that you think you've found some really good settings, you can click save and it will save it into the setting overrides. But just be wary, next time you start, that will always have those settings. So I'd recommend being cautious of saving them. I think the current defaults are what we recommend, but you do have the option of tuning them if you want to try and squeeze a bit of extra performance out of the PID controller. So that's all I'm going to talk about with the PID controller. I hope it sort of helps explain a bit more of how the control system works and what to look for to ensure that the system's operating as expected and performing well. And we're constantly trying to improve the tracking, but we think we're pretty close to the hardware limit of what the Polaris can do. From the data we've looked at, we've got probably a 2 to 3 times improvement in the tracking performance, and it's doing things that it was never doing previously. So I'm pretty pleased with how it's turned out. That's all I've got for today. I hope you enjoyed the deep dive into the PID controller and the motion control system. We'll see you next time. Bye for now.